Hey everyone, so we are now doing 3.13 polar trigonometry and polar coordinates. So what is a pole? So as you can see, this is the polar axis. It's kind of a series of concentric circles. The pole is going to represent our origin, right? So here on the polar axis, we have this is our starting standard line for a angle. And then here's our terminal. And then we have a random point on one of those circles. And then we have our theta here. Well, in a polar coordinate, it's written as you can see here, r comma theta, where r, which is our radius, is our length, while theta represents our distance. So if I want to convert, or if I'm looking for plotting points, I should say, here's how you would plot a polar coordinate. So we have 2 comma pi over 6. So I'm going to look for my pi over 6. That's on this line right here. Let me highlight it. There's my 2 pi over 6. Now, for my point, right, I need to go 2 circles, or you can see the tick marks here, but 2 circles towards pi over 6. So that represents a positive x. I'm moving towards the pi over 6, right? If I have a negative, like in this example, I'm actually going to move away from my y value. So looking here, my unit circle is a little bit small, but here's 7 pi over 6, right? So if I am at -3, I'm going to start at the origin, right? And I'm going to move away from it. That's how I move my negatives. I'm going to follow along the path of the pi over 6. So 1, 2, and 3. Okay, so that is how you would plot polar coordinates. So now we're going to look at naming some. So here I have this point right over here. Well, the obvious point I'm going to say is 4 comma 5 pi over 3, right? That's the most obvious. I move in 4 circles and I'm going towards 5 pi over 3. But I can also say that I'm moving away from this 2 pi over 3. So if I'm moving away from it, I'm going -4 comma pi over 3. And remember, you're starting at the origin. So when I'm moving away or towards the value, it's starting from that origin, okay? And then, well, what's another one I can do? Well, if I want to say that I'm going backwards, right, then I can say that I'm also going, oh wait, this is -pi over 3. So we're going in all the different directions. And then once again, this is -4. I actually did the explanation for this one. 2 pi over 3. The pi over 3 that I just did, this one here, is actually going to be a +4. Let me explain that one again. Because what I did was I accidentally explained the 2 pi over 3. I got ahead of myself, right? Well, 5 pi over 3 is if I went the normal, regular way for my angles to go, right? They go counterclockwise. So this going this way is how I got there. But now let's say I go in the opposite direction. Let's say I'm going clockwise from it. So that's going to be in the opposite direction. Well, that's going to give me to pi over 3, but it's going to be -pi over 3 because I'm going in the reverse, right? Rather than going clockwise, I'm going to go counterclockwise, and my corresponding angle in the first quadrant is pi over 3. But because I'm going in the opposite direction of a typical angle rotation, it's going to be -pi over 3, but I'm still going to be moving 4 towards that point, okay? Now, I already explained the -4 comma 2 pi over 3, And then it's the same idea except with 4 pi over 3. So the opposite of 2 pi over 3, if I went in the reverse direction, is going to be at the 4 pi. And once again, that one's going to be a negative because I'm going in the opposite. And then it's going to be negative 4. Okay? So those are my 4 points, 4 different ways that I can name that point on my graph. Now, what if I want to convert polar functions to rectangular coordinates? Now, rectangular coordinates are what we are used to. Rectangular is our x comma y, right? Because when you look at a normal grid, the normal grid does look like a bunch of rectangles, right? And yes, I know what you might be thinking, but Ms. Perdomo, those rectangles, as you call them, are really squares. Well, remember that squares are rectangles, right? So how can I convert this? Well, if I take the radius for x and I multiply the radius times the cosine of theta, that's how I'd get my x, right? And it makes sense because on my unit circle, remember that the x value is cosine while my y value is sine. So it's going to be the same thing for sine or for y, except it's going to be sine of theta. Okay? So let's go ahead and try converting. Well, all I need to do is say, okay, in this example, I need to get my x value. I need to go ahead and say 6 times the cosine of pi over 3. Okay, well, according to my unit circle, pi over 3, this cosine of pi over 3 is 1/2, which equals 3. And then for the y, it is 6 of sine of pi over 3. And remember that the sine of pi over 3 is square root of 3 over 2. So when I go ahead and do that, my 6 cancels out with a 2, leaving me with 3 square root of 3. So my value, when I go ahead and rewrite this in the proper rectangular coordinate, is going to be, I don't know why that weird thing happens. Okay. It is going to, let's try that again. It is going to be 3 comma 3 square root of 3. And that is my 6 comma pi over 3 in polar coordinates converted into rectangular. So I'm going to give a moment for you guys to try out the next one on your own. If you are watching this, make sure you pause the video so that way you don't get spoiled on how to do it. So it's the same steps, right? I'm going to go ahead and say x is equal to 4 times the cosine of 5 pi over 4, and y is the sine r or 4 times the sine of 5 pi over 4. Well, conveniently, right above us, we do have a unit circle. So I can easily see that 5 pi over 4 is in quadrant 3, which means that both of these answers are going to be negative. So it's going to be 4 times the negative square root of 2 over 2, which is going to equal negative 2 square root of 2, right? And it'll be the same thing for the y. That is the one very convenient thing about pi over 4s. They are the same thing. They're negative square root of 2 over 2, which is negative 2 square root of 2. So again, this one is negative 2 square root of 2, comma, negative 2 square root of 2. But now let's say I want to switch back and I want to go over to polar coordinates, right? Well, to figure out the polar coordinates, it's a little bit more interesting to do. So you have, let's just draw a quick little graph here. Let's say I have my triangle, something like that, right? Well, I have my radius here, my theta, my y, and my x, and I can say that x squared plus y squared equals the radius squared. So once again, I'm just using that Pythagorean theorem. So when I have the Pythagorean theorem worked out, I can say that r, by square rooting both sides, I can say that r is equal, I'll write it over here, r is equal to the square root of x squared plus y squared. Now, to find the theta, what I would need to do is the inverse tangent function of y over x. Okay, that would give me the information. Right? Remember that we're not using the radius. We don't know what the radius is until we find it. So in order to figure out what theta is using x and y coordinates, well, the only thing you can do is find out, use the trig function of tangent, right? Tangent is the one that would give you that value. And in order to do that, you need to do the inverse. So you need to kind of undo the tangent. So let's try it out. Here we have r is equal to the square root of negative 3 squared plus 5 squared. And then theta is going to equal the inverse tangent of 5 over negative 3. So this kind of question, unless the values are very, very simple, this type of question would only occur in the calculator because there's no way for you to do the inverse tangent without without a calculator, unless it's a very obvious value. Okay, so I would have the square root of 9 plus 25, which is equal to the square root of 34. Not very nice looking, but you know, what else can you do? So when you do this, when you do the tangent of the inverse tangent, you get that it equals to negative 1.030. So now the problem is, if I were to graph this, let me just do a little graph over here. If I were to graph negative 3 comma 5, my point would be somewhere over here, right? But this value, this tangent value, actually exists somewhere in quadrant 4, which doesn't work for me, right? I need it to be in quadrant 1 or quadrant 2. So in order for that to happen, I need to do a complete 180. So I need to go ahead and I need to add pi to that value. And when I do that in my calculator, I get that my theta is equal to 2.111. So, and I will try and fit this in somewhere. I'll do it in a different color. My polar coordinates are the square root of 34, comma, 2.111. I know it's not very pretty to look at, but those are the polar coordinates. So go ahead and pause the video so you can try the next one on your own. And I'm just going to go ahead and get started on it. Well, the radius is going to be the square root of 2 squared plus negative 6 squared, which is the square root of 4 plus 36, or square root of 40, right? Now you can leave it at 40, but remember that if this is on the FRQ section, you do need to convert square root of 40. It needs to be in a simplified radical. So that means I have to come over here. I do my 40. That's going to be 8 times 5, which is 2 times 4, 2 and 2. So I have a set of 2's, and the leftovers are 5 and 2. So it's 2 square root of 10. Okay, so that is my R. So I'm going to write that in over here. 2 square root of 10. And then I need to figure out my theta. I think the theta is the less enjoyable part of this, right? And by the way, for the previous example, the negative 1.030, I forgot to mention that the other very important part is that we are given a domain of 0 to 2 pi. So negatives are obviously not going to be in that domain. So that's also why we had to go ahead and add that pi. Okay, so let me continue over here. I'm going to have the inverse tangent of negative 6 over 2. And when I plug that into my calculator, I'm going to get a value that's not going to be within my domain. So I'm going to have to do a plus 2 pi. Let me see if I can get that value to you. So it's going to be I'm just doing this in my calculator. So 1 moment. Negative 6 divided by 2, which is actually going to give me a negative 71.565, which is not going to work for me. I don't even know if that's really what it should be. Let me make sure that this is going to work. Something clearly went wrong with this calculation. That is a way too big of a number. Negative. Well, the correct value is supposed to be 5.034. I'll have to check in with my graphic calculator. I don't have it with me right now. So my final coordinate is 2 square root of 10, comma 5.034. Okay. Now let's go ahead and talk about the complex numbers, right? Because we can't have fun without complex numbers. So absolute value of complex numbers. So here we have our very nice looking Z, which is the imaginaries. So I'm going to go ahead and draw in a triangle. Right, there's a triangle right there. And I'm going to have X, Y. Oh, I'm sorry, I labeled it wrong. That's supposed to be R. R, X, and Y. So notice that this is in the real area, right? Notice how it says here real, right? And over here, I've got a little guy hanging out over here, right? So if I want to name the point on the imaginary line, I need to look over here. So I have A plus BI. Okay, well, A plus BI, that's going to be, if I look over here, I'm at negative 4 minus, because I'm going down, 3I, right? So that is our imaginary. Now, let's say I want to convert rectangular complex numbers into polar form, right? Well, my r's and theta are going to be the same. So it's going to be x squared plus y squared. And then my theta is going to be the inverse tangent of y comma x, right? Now, what I'm going to have to do is I need to kind of ignore the I, I'm sorry, in these complex values. So to find my r, I do -3 squared plus the square root of 7 squared, which is going to be 9 plus 7, which is the square root of 16, which is just 4. Okay, and then for the for the theta, it is the inverse tangent of square root of 7 over -3. So again, what I'm doing is I'm kind of ignoring the values that I have, right? So again, this value is going to be somewhere in a different quadrant. So what I would need to do is add pi at the end because I'm in the opposite, like I was in the first example we had to do. And so I get that theta is equal to 2.418, meaning my coordinates are 4, 2.418. So really it doesn't change too much, right? Because the values are now different, right? They're different, they're complex, but essentially I'm going to kind of work with the same thing, okay? So with that, and then I'll let you do the next one. And then to convert the polar to complex, right? My x is going to be the same thing. It's going to be, oh, and this is polar complex values. So x is still going to be r cosine of theta, and this is still going to be r sine of theta. Here's my r, here's my theta. So it's going to be x equals 3 cosine of pi over 3. And then y is going to equal 3 sine pi over 3. So in x is going to be 3 times 1/2, which is 3/2. And then I'm going to have 3 times the square root of 3 over 2, which is 3 square root of 3 over 2. Meaning that when I write this, it's going to be written as 3 square root of 2 plus 3i square root of 3 over 2. So this is the value that's going to get that I because of the fact that it is, you know, complex, right? It's going to be a complex. So I'll let you try this one on your own as well. We can go over that in tomorrow's, but that is the end of 313.